Hi everyone. Before I write the first fundamental theorem of calculus on here, I'm going to sort of review where we left off in class. This is the one from the packet. It was on page 13. So I gave you f of x to be this special integral. You came up with the equation of the integral. You came up with f of x as 2x. And you also wrote down on that page 13, that 2x is the antiderivative of 2. So one more time, if I ask in class, what is this special integral equal? You're going to say this special integral equals the antiderivative of 2. Let's make sure you're okay with that. If this is the antiderivative of 2, that means 2 is the derivative of 2x, right? If you take the derivative of 2x, you're going to get 2. So 2 is the derivative of 2x. 2x is the antiderivative of 2. So this special integral represents two things. It represents the area function. And again, the area is a function because the upper limit's changing, so it represents the area function. And it also represents the antiderivative. Then in the next step, I had you take the derivative of this antiderivative, and obviously you're going to go back to where you started. So I made you find the antiderivative, then I made you take the derivative of the antiderivative, and obviously you just went around in circles. All right, this is page 14, this is number 2. We did this in class, we started it, and some of the arithmetic I don't have on here, but I did it on the board, so I'm hoping you're okay with it. The function given was t plus 1. Here are the bounds from a to x. Here's my area function. Again, my area function equals the integral from a to x of t plus 1 dt. And this integral represents the area function. This integral also represents the antiderivative of t plus 1. So all of this right here, this is the antiderivative of t plus 1. So you did all this work, well, you found the area of the trapezoid, you did all this work to find the antiderivative of t plus 1, and then I made you take the derivative of this. You took the derivative of the antiderivative, so of course you're going to go back to what you began with, which was x plus 1, but it has to be in terms of x because this function is in terms of x. This is where if you have the incorrect variable, you'll get points taken off. All right, so let's write the fundamental theorem of calculus. It's the first one because there's a second fundamental theorem of calculus as well. So I'm hoping you're writing this in your notebook. I'm on section 6.4. It's the first fundamental theorem of calculus, and this is part 1 of the theorem. Part 1. I'm going to write it here. This is part 1. Part 2 we'll do in class the next time I see you. Part 2 is easier than part 1, so let's get the more difficult one out of the way. So we're going to let f be continuous on this closed interval, and this is what capital F equals. So, and big F of x equals, there's that special integral from a to x, and here's my little f, and I have to use another variable. I can't use an x. So f, this little f refers to the integrand. Let little f be continuous on a closed interval, and then capital F of x equals this special integral. So now, tell yourself that you know what this integral represents. You know what f of x represents. It represents the antiderivative of this. The next step is, or this is just the given information, then the first fundamental theorem of calculus says that if I take the derivative of this, so then, should I just do then? I'll start with then. Then the derivative, I'm using Leibniz's notation, the derivative of this entire integral, using Leibniz's notation, the derivative of this entire integral equals So look, taking the derivative in terms of x, because this function is made up of x, and this has to be a different letter. We know that this entire integral represents the antiderivative, or it represents the area function graphically. So if I take the derivative of some antiderivative, like I don't know what the antiderivative is, I know but that I take the derivative of the antiderivative, that I just get the integrand, but in terms of x, because I was taking the derivative in terms of x. That's all the first fundamental theorem of calculus says. It helps you understand. Please jot yourself a note that you can write it here, or you can write it here, that this represents the antiderivative of little f. That's what big F of x equals. It equals the antiderivative of little f. This theorem is just showing and it's explaining that the antiderivative and the derivative are opposites of each other. They're inverses of each other. It's like square rooting and squaring, that when I take the derivative of an antiderivative, I get back the integrand, which is what I began with. So let me do an easy example of this theorem, and then the harder example we'll do in class when I see you. So here's an example. If they want you to find the derivative, I'm going to stick to, I'm going to stick to x, of the integral from 7 to r, 1 over 1 plus r squared dr. I'm so sorry, I made a typo. If that's an x, that has to be an x. They both have to be an x. If that's an x, that's also an x. I just made up r for my integrand. I made up r for this. And now we are not going to take our time. We're not going to waste our time finding this. We're not going to do what I made you do on page 14. You spent all this time, because I asked you to, and I'm hoping it was good practice. You spent all this time using the area of the trapezoid formula to come up with this expression, which represents the antiderivative, and then I made you take the derivative of this, and you went back to where you began. So I am not going to ask you to go find this antiderivative. We are not graphing 1 over 1 plus r squared. We are not making a table where you start off with like x is 7, and then the area, we'll just call it a of x, is 0. When x is 8, like you'd have to graph this and see what shape it makes. We are not doing all that. We know that when I take the derivative of this, it's just going to equal 1 over 1 plus x squared, and that's it. Because this represents the antiderivative, when I take the derivative of the antiderivative, poof, everything disappears. The derivative sign disappears, the integral disappears, the dr disappears. It's just the integrand, but it's made up of x because this derivative was in terms of x. Okay, I'm going to put some textbook pages that I want you to do, and the other thing I want you to do is I would like you to go to your textbooks, and there's an example that's not easy on page 305. Here's the example. I want you to try every question on here. Look, here's that special integral. I want you to try all these questions. This is the graph right here of f of t. This is not